right, so we are starting chapter 7 today, and we're just going to cherry pick some of the lessons out of this that I think are kind of extra important. And so there's 3 lessons that we're going to hit out of chapter 7. And the first one is going to be the basics of counting theory. You may or may not have seen this before, kind of just varies by Algebra 2 classes. Now, counting theory really revolves around figuring out the number of ways that you can do something. And that's kind of a key part of probability, which is what we're going to do tomorrow. So we're kind of learning some of these counting principle properties so that we can use them tomorrow. So this first one is called the fundamental counting principle. And it's sort of the most basic one that, and the way I have it written here, it says if there are m ways to do one thing and there are n ways to do another, then you would have m times n ways to do both of them. Now, when you're doing these different counting principles, each one kind of has its own little specialty of when you would want to use it. And there's some key characteristics that decide that for us. So looking right here at these 3 kind of situations or restrictions, this is going to be important. So the order does matter, repeats are allowed, and you can customize with some sort of restriction. So that's kind of my key one that I pay attention to. Like if I have any customization that I need to be doing, I'm going to be doing the fundamental counting principle. Let's take a look. The most generic type of problem that you probably have done clear back in middle school is if you have 4 pairs of shoes, 12 shirts, and 8 pairs of shorts, how many different outfits can you create? And all you do is that's your M and your N, and I actually have a third option going on. All you have to do is take your 4 times your 12 times your 8, and that's going to tell you the total number of ways that you can rearrange that. So in this case, that means there are 300. Oh, my pen stopped working, sorry. 384 different outfits that we could create just by multiplying those options together. Okay, let's make it a little bit more advanced of what we're going to be doing in this class. It says, how many ways can you answer a 10-question multiple choice quiz? And apparently there are 5 options, A, B, C, D, and E. How many different ways could this play out that you could do this quiz? And when I'm doing fundamental counting principle, I kind of like set up dashes and I say, all right, this is my first question. This is my second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. 10 questions. And then I look at each one and I'm basically doing the fundamental counting principle, but I have to make that decision on each question. So how many options do I have for the first question? Well, I would have 5 options for the first question. It could be A, it could be B, it could be C, it could be D, or an E. Now, remember we said repeats are allowed. So when I come into question number 2, it's totally fine if I chose A on the first question. I might still choose A for the second question. So that means I would still have 5 options for question 2, and I would have 5 options for question 3, 5 for this, and all the way down. Now remember, what you're doing between all of these is you're multiplying these. Now I get kind of lazy with putting that dot in there, and when I start doing my dashes, I just know that means I'm going to multiply in there. Now I'm certainly not going to type that in the calculator like that. That's ultimately just a 5 to the 10th power. And I'm kind of doing the math in my calculator as we go. Oh my, that's a lot of different ways. So, and don't be afraid, you are going to definitely get some big numbers on these problems today. So we have over 9 million, almost 10 million different ways that this test or quiz could be answered. All right, let's look at how many seating charts can I create for our class. All right, so let's pretend there were 20 students in class today when I did this. And so that means I have 20 different seats and I'm putting students in them. Now, the order that I place them does matter. That was one of the restrictions on that previous slide, because putting Bobby in seat 1 is different than putting Sally in seat 1. You know, where this is the whole question is how many different ways can I place these students in the class? So ultimately, I have 20 students, and I'm not going to write all those. And then how many students would I have for the first seat? Well, I would have 20. I have 20 kids there that I can place there. But now here's what's different this time. Since I've already placed somebody in that first seat, I don't have 20 for the second option. Now I only have 19 options to place in this seat. And now 2 of them are used up, so I only have 18 for this one, 17, 16, and all the way down. And again, I'm not going to do it, but that gets pretty lengthy. Now I don't have this nice shortcut of 5 to the 10th to write this all out. This is going to get very tedious to try to type in the calculator. So, well, actually, I do have a shortcut. It's called factorial. Anytime you take a number and you are multiplying it by every number below it, that is called factorial. And it is notated with like an exclamation point. And I don't know why that seems like a weird thing, but that stands for 20 factorial, meaning I want to take 20 times every number below it. In your calculator, this would be under, and you're going to want to get familiar with this screen on your calculator. You're going to go to your math menu and then scroll over to probability. And you can scroll backwards. It does wrap around. That saves you a few keystrokes. And then you're just going to see all these different options. And I forget which number it is, but one of them shows this little exclamation point thing. And so you're just going to type 20 and then go to that menu and type in that factorial button. And oh lordy, huge number. It's even in scientific notation. Okay, why am I freaked out? I already told you it's going to happen. So I have 4.3. I guess I'm just going to go 2 decimal places times 10 to the 18th power is what I'm getting here. Now, if you don't have your calculator handy, you need to go grab that, pause the video and go get it. You're going to want to use that today. Okay, this next one sort of has to do with how we're kind of always having to update our passwords, or, and I guess you're kind of young, you don't realize the progression of how this has worked. You know, you used to be able to maybe just have a 6-digit or a 6-character password, and now they keep adding more and more. It's got to be longer, it's got to have special characters, it's got to be capitalized, it's all the stuff, because it has to do with how quickly they can get hacked. And so we got to see how many different passwords could there be created if I had 10 digits. And then I'm going to put restrictions on these. And the more ways, the more passwords that could be created means the less likely it would be hacked. So let's pretend you cannot repeat digits. All right, so it's 10 digits. So I've got these 10 numbers here, and I'm going to get it started, but let's see if we can just notice the pattern, and then we'll know what to do. So 10 digits. All right, well, it could be a 0 through 9. That's 10 different possibilities for that first character. Now, since I can't repeat digits, I would only have 9 options for the next one, and then 8, 7, and all the way down. So this would be 10 factorial. And maybe what I'm going to do today, I said grab your calculators, and we will need them, but I maybe won't calculate every single one of these. Let's just know that I would go to my calculator and take 10 and go to that probability menu to do the factorial. What if you could repeat digits? And again, I'm going to go out there until there were 10 of them. If I can repeat, I have 10 options for the first, but I would still have 10 for the next, and 10 for the next, and 10 for the next, all the way down. This would be 10 to the 10th power because I have 10 digits in there, which definitely is going to be a lot bigger because those numbers are, well, I could actually write that one. That's just going to be 10 zeros in here. I think I counted that right. Okay, so that's going to be a lot more than part A up there. Okay, now I'm going to throw more restrictions at you, and I love the fundamental counting principle for these special scenarios and restrictions. Now I have 10 digits again. I should make an example where I don't have to have 10 of these. Okay, there we go. The first number cannot be a 0 or a 1. All right, so that means I would only have 8 options for the first character. Now I am allowed to repeat, so that means I'm back to 10 options for everything after that. All right, so that's going to end up with 9 tens there instead of 10 tens. So that's going to be an 8 with 9 zeros. All right, so then you're at 8 billion different passwords I could create. Now, what if we say the password must be an even number and I can repeat? All right, here we go. Last example. Got 10 digits here. For this to be an even number, what's going to have to be the case? Does the first number matter? Nope. I would have 10 options for that. Does the second number matter? Nope. I could have 10 for that. I could have 10 for all of these, right up until you get the very last digit. And for the whole entire number to be an even number, that means this last digit has to be an even number. And there are 5 numbers that I could plug in that would create an even number. So in that case, I would have 5 billion different passwords. Okay, so just again, this is the one that you're going to want to use anytime I start throwing special circumstances at you. This is going to be a good method to use. Let's try one where there's not quite as many digits, although there's still 8. So let's say you're watching this horse race. There's 8 horses in a race. How many ways can you choose the placement of all 8 of them in order? Okay, this is a classic gambling kind of question, which is where probability comes into a play a lot. You're doing everything with the odds, or the probability of something happening dictates what the payout on some sort of a bet might be. So for me to pick all 8 of these horses in the right order, how many different ways could that play out? So how many horses would I have for first place that I could choose from? All right, I could choose 8 different horses. But in this case, there's no repeats, because once I've chosen one of those horses, I can't put them in the mix again. So now there's only 7, 6, 5, 4, 3, 2, 1. Okay, which is just 8 factorial. Now that's such a huge number, that's actually not a viable bet. That's not one out there. But what there is a common bet would be to pick the top 3. And so I've got these 8 horses. I got to pick who's going to place in the top 3 places. So I still would have 8 horses to choose from for the first, and then 7 for second place, and then I'd have 6 for third place. Now that's not near as big of a number, so way fewer ways for this to happen. There's only 336 ways for that to play out. Now, we could do this. Now we're kind of leading into something here. So if I wanted to write this using the fundamental counting principle, that would be this right here. I would take 8 times 7 times 6. If I was going to do it as a factorial, it wouldn't really be 8 factorial, because I'm only using the 8, 7, and 6. However, what I am doing, I could write the 8 factorial, but I don't want the whole back end of this, of 8 factorial. So what I can do is I can actually divide by what I don't want, which is 5 factorial. If you think about what that would look like if I wrote it all out, I would have an 8, 7, 6, 5, 4, 3, 2, 1. This would be a 5, 4, 3, 2, 1. I would cancel the 5s, the 4s, the 3s, the 2s, the 1s, and all that would be left was this 8, 7, 6, which would be the fundamental counting principle. Now you have to decide which of these is the quickest way to type into your calculator. If it were me, I would just do the 8 times 7 times 6. That's faster than messing with getting into your probability menu. However, if this list of numbers was a lot longer, maybe it was 7 or 8 digits longer, maybe then I'd rather go to the probability menu in my calculator and do this. Now, what we just did there is a very common scenario, and we call it a permutation. It's an arrangement of objects. So we're saying like there's n objects. In that last case, there were 8, and I'm selecting R of them to put in order. So in that last example, I was trying to pick 3 of them to put in the proper order. Now, when you're doing permutations, the order matters. Getting first place is not the same as getting second or getting third. So the order I picked those horses definitely matters. Also, no repeats are allowed. As we showed when we did our fundamental counting principle, it had to start decreasing because I couldn't pick the same horse more than once. This happens often enough. We have a special notation for it. It's a special operation in our calculator. This is called permutation of n items choosing R. So n permutations choose R. And the way we did that is we took this, remember that I'm just going to throw this out there because it's, don't write this on your notes necessarily, but it was an 8 here and we were choosing 3. So think about what that means. I took 8 factorial right here. And then I remember I divided it by what I didn't want, which was 5 factorial. That 5 really just comes from taking how many there are and subtracting how many I'm using. So this would be 8 minus 3, which is 5 factorial. Now, I told you you could type this in your calculator, 8 factorial divided by 5 factorial. But you know what? We're not going to do that because there's a special button in our calculator that actually does that very thing. So go ahead in your calculator. Let's get back into, well, I usually think it's easiest to type the 8 first. So hit 8. And then go into your probability menu. Again, that's in math, and then over to probability. And one of those options is this P, the permutations. And if you select that, then you can type in the 3, and you can do 8 permutations choosing 3. And if you just hit enter, you're going to get the same answer that we got earlier. Now, is that faster than just doing 8 times 7 times 6? I'm going to say still no. But man, if I was choosing more than 3, if I had a 6 or a 7 here, something like that, I would definitely be choosing this option in my calculator to figure that out rather than typing those numbers all in. All right, I've got another problem here that we can use the permutations and the fundamental counting principle, tying this all together here. So on this one, it says, what if your password is not 10 digits? Because of course, I'm tired of writing out 10 dashes. Instead, it's only 6 digits long. But I'm still not going to allow any repeats on it. So then if it's only 6 digits, fundamental counting principle would look like this. I would have 10 options for the first character, anything 0 from 9. But since I'm not allowed repeats, it's going to have to start declining. This is what it would look like if I was doing, oh, I missed my 5 in there. Sorry. Okay. This is if I was doing fundamental counting principle, that's what I would type in. If I was going to write it as a factorial, it feels like it should be 10 factorial, but I'm missing, or I at least don't want, the rest of this 10 factorial, which would be the 4, 3, 2, 1. So I would divide by the 4 factorial. If I were to write it as a permutation, it would be permutations, 10 items, and I'm choosing 4 of them. All 3 of these are fair game, but you need to be smart about which method you use, or you're going to be taking forever on your homework and you're going to run out of time on your test. So I guess be familiar with all 3 of those methods. Okay, let's see what we've got here. How many ways can we select a president, a vice president, a secretary, and treasurer from a class of 22 people? Okie doke. So just some key things. I can't repeat here. You can't be president and vice president. You only get to be one thing. Also, the order is important on how we select people because being president is not the same as being the treasurer. So where I slot somebody in that mix would matter. Okay, so I'm going to start off because I can already tell my number's kind of big with a 22. So I'm going to do permutations of, I have 22 students, and how many of them am I choosing? 4. I've got a president, vice president, secretary, treasurer. Okay, I'm not going to mess with typing that in the calculator. I'm just going to try to keep us moving, but know that you will, on your homework and everything, you will type that in and get an actual value. Okay, I lied because I think I'm going to need that number on the next slide. So here I go, 22, and I'm choosing 4. Okay, here are how many different ways I could set up these class officers. 175,000 plus different ways of creating this class officers. Now, let's try something kind of similar. It says, how many ways can we select a committee of 4 people from a group of 7 people? Okay, so I guess I'm done with that class of 22. I'm starting over. So I've got 7 people here, totally different scenario here. Got 7 people standing there. I'm going to pick 4 people to be on a committee. So that would look something like this. Permutations of, there are 7 people, and I'm going to choose 4 of them. But here's what's different in this scenario. Think about this with me. If you were picking a committee, I'm not saying, hey, you're in charge of the committee. I'm just saying, hey, will the 4 of you be on a committee for me? And you're just going to work together to do something? If that's the case, do I really care the order that I'm choosing people anymore? Since nobody is really in charge, the order I pick them no longer matters. I set this up over here on another slide. It says, what about like when I choose Abby, Bella, Charlie, and Danny, specifically A, B, C, D to make my life easy here? Is that a different committee than choosing Bella, Charlie, Abby, and Danny? Is that different? No, that is the exact same group, same committee. So in other words, when I come up with that number, whatever that was, okay, so I lied about the 22. I think what I'm going to need is the 7 permutations of 4. Okay, that was 840. If you want to write that on the previous slide, there were 840 different groups that I created, but that is way more than what there really is since there's all this overlap. Every single one of those groups that I picked got overcounted. So I've got to figure out in this particular group, the A, the B, the C, and the D, how many ways can I rearrange this? Because however many ways I rearranged it is how many times it got counted. So I'm going to break this down to these 4, A, B, C, and D. How many options would I have for the first person? Now, again, assuming these are the 4 kids that are chosen, how many ways can I rearrange those 4? Well, I'd have 4 people that I might have chosen first, and then it would go 3, 2, 1. So there are, what is that, 24 different ways of creating this particular group, which means every single group I chose got overcounted 24 times. So what do you think I need to do with my 840 over here? I need to divide it by 24 because there's that much overcounting going on in this problem. If I divide it by 24, there's really only 35 committees that I could have created. So what is different on this problem based on what those special characteristics I told you had to have? The order is no longer important. Everything else, the horse racing, the password, the order that you pick those items definitely would make a difference. If I'm choosing a committee, that no longer matters. This is not the only type of situation where that happens. It actually happens quite often. If you're playing cards, which we will do tomorrow, well, we're not going to play cards, don't get your hopes up, but we're going to talk about playing cards. And like when you're dealt a playing card, you immediately sit there and rearrange them in your hand. It doesn't matter the order that you got those cards. And so this has its own special process to work with. This is no longer called a permutation. It is now called a combination. So you're selecting a subset of items. So I had the 7 people and I selected a subset of 4 people. So there's N objects and I'm choosing R of them. That's still the same deal. But the big difference here is order no longer matters. I still cannot do repeats for this to work. It's still going to sit there and decline. But instead of a P, now we're going to use a C. Look at how this is set up. This is the same thing that I did with the permutations. This right here was the permutations. But remember on that previous slide, I had to come back and I had to divide by 24. And that 24 was really just 4 factorial. So again, I don't know that you need to write this on your notes, but it was 7 people and I was choosing 4 of them. So I did the 7 factorial divided by the 3 factorial. That got me the 840. But then I came back and divided by the 4 factorial, this number here, factorial. Again, this is how it works. But what we really need to, what we're going to do is we're just going to go to the calculator, because in your probability menu, you now also have an option for combinations instead of permutations. So then you can choose that one instead. And ideally, if you do that, you'll get a 35 when you do combinations of 7 items choosing 4. All right, as promised, let's talk about some playing cards. So in blackjack, you are dealt 2 cards. How many different hands might you end up with? Okay, so when you play blackjack, okay, we will talk more about cards. Maybe you're not a big card player. There are 52 cards in a deck if you're not using the jokers. And in blackjack, you don't use the jokers. Now, as I mentioned, when you're playing cards, the order doesn't matter. So you can't do that fundamental counting principle anymore. You can't do permutations anymore. Both of those scenarios, the order is important. I'm playing cards, order is no longer important. I'm going straight to my combinations. So when I set this up, there's combinations, and I've already told you there's 52 cards in the deck, and you're going to be dealt 2 of them. And then we figure out, well, how many ways can you do that? So I'm going to my calculator, it'd be 52. And then I go over to that probability menu, and I choose combinations this time, and I'm choosing 2. So there's actually quite a few ways that can happen. Let's look at this next example. It says a district-wide group of 24 has 14 Mays High School representatives and 10 Mays South High School representatives. We're going to send 5 members from this district-wide group to a retreat. How many ways can we select 3 MHS representatives and 2 Mays South representatives to attend? Sort of feels like that would be the appropriate representation. So how many ways could that play out? All right, now this time I have 2 scenarios. I have to look at the Mays High. How many different ways can I choose 3 of them? And then I have to look at Mays South. How many ways can I choose 2 of them? So it's a double combination situation here. So I'm going to start with Mays High. And I have 14 students in that group, and I want to choose 3 of them. And I'm going to also have to work with it's almost like a fundamental counting principle. So it's how many ways can I do this, and how many ways can I do the next scenario? So you're going to end up multiplying these numbers together. Now I have 10 Mays South students, and I want to pick 2 of them. Notice I never put a 5 anywhere. because the 5 is really just created from the 3 and the 2 that I have here. So the 5 does not go in here at all. So go into my calculator, 14, choosing 3. And then I'm going to take that and multiply it by 10, choosing 2. So I got a 364 and a 45 on that, which is going to get me a total of 16,380 different, whoa, what was that? Different groups that I could send to this retreat. Okay, so what I'd like to do here is I would like to put you a little bit on the spot instead of me just telling you what to do every time, because I usually hear that the trickiest part of this is knowing which method to use. Once you know which method, it's not always that hard, but knowing what do I do in this scenario, what do I do in this scenario. So what I would like you to do is go ahead and pause the video, and I want you to go through these 4 questions, and then there's more on the next slide. Go through all of them and just try to set them up. See if you can tell this is a fundamental counting principle. I'm going to do dash, 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 dash. Or is it a permutation, because it's going to be maybe another better option to choose the permutation option on my calculator? Or is it a combination where the order is not important? Okay, so no cheating. Pause the video and just set these problems up. You don't worry about plugging them in yet. All right, here's how I set these up. The first one, I'll just kind of explain this. The first one, it says how many different lineups can be created. Well, that's the whole thing, is how many different ways can I arrange these people? And so that's definitely, order is important on the order that you're selecting them. So that's a permutation situation. Now, you could have done the fundamental counting principle, but that would have been a whole lot of dashes and a whole lot of multiplying in your calculator. Okay, the second example, they talk about picking people for a city council. Nope, they don't talk about anybody holding a special position. Nobody's the president, nobody's the vice president. We're just picking people. That's a combination. Same thing with the third one. It's a card problem again. I'm going to rearrange those cards. I don't care the order that I get them. Got to be a combination. The last one here, they're giving you restrictions. Anytime I start giving you restrictions, you're going to have to start writing it out and listing out how this plays out. So there's 26 letters. It did not say that they can't be repeated, and probably, I'm guessing, some common sense, you've seen enough license plates that yes, you can definitely repeat characters on a license plate. So it went 26, 26, 26, and then I went to numbers 10, 10, 10. I guess I'm not going to take the time right now to calculate those. You'll have plenty of practice on your homework to go type in stuff in your calculator. On these last 2 examples, all right, there's some key phrases here. Sebastian has 8 courses to choose from to fill 4 blocks in his schedule. How many ways can he arrange his schedule? So the fact that he's looking for a particular arrangement means having math first block is not the same as having math second block. That's considered a different schedule. So that's a permutation situation. Now, I should throw this out here. If you happen to do, here's your 4 blocks, and you said you had 8, and then you had 7, 6, and then 5, because you can't repeat, that would have been an acceptable answer as well. It would have gotten you the same answer as if you had done the permutation thing. And 4 numbers is not that hard to type in your calculator, so maybe you opted for that. That's okay. Okay, the last one is that double up thing where you've got females, you've got males, and you're trying to get 3 of each. So then you're going to do the combination for the females first, and then you do the combination for the males next. Okay, that's all I've got for us today. Hopefully that all makes sense, and you can just fly through your homework. Good luck.